I am the bridge between Maria Christina and Molly, meaning I'm going to talk a little bit about that roadmap that Maria Christina introduced yesterday, and then I'm going to go through how to actually do the things that Molly described within R. And that actually reinforces what Maria Christina brought up in the first place, which is you can use these measures to detect madness. If some of these network measures are not looking healthy or good, this is a detection that there might be a data problem. So first off, because it's still, I mean, it's 10:30, but it's just had a conference, things like that, or just had a presentation. Let's get to the Dropbox. We're going to go to day 3. And we have 2 labs today, so we're going to go to Network Descriptive Stats Lab. And I want you to download into whatever folder you're downloading all your goodness. The descriptive analyses. You probably already have this file from the first lab. These plots, just for your reference. And these 2 are data sets. Okay? So I'll give you a second or 2 to get that down on your machine and good to go. On transition, I'm going to bring stuff up on my side. So I've already loaded my code. I'm going to get rid of this untitled because that's confusing. And I'm actually going to read in my flow. That's Florentine families, just to be clear. And we'll probably get to it. There's a lot going on in this lab, so it was action-packed. So we'll go through this, and we may hit all the things, and we may not. And if we don't, you can follow up with me. But how do we read in an R file? Oh my goodness, an R file. You know, by the end of this, you're going to the data that we've been manipulating and you've had to do all those steps, you're going to get to save it and never do that again. And that's going to be a great moment. So we can open file. And we can go, there's our Florentine edges. That's our edge list. Do you want to load this into your global environment? Yeah, sure. And it's down here now. I had some help with my friends, right? Help with this display. And then I'm going to do the nodes list as well. So I'm going to open my file, and I'm going to get there's my nodes. OK. So this is example data. I'm pretty confident I'm not going to clear stuff up because I just loaded things in. I probably should have done that. I'm going to load my packages. My graph is later. OK. And we're going to primarily work with the SNA module of StatNet. So I'm putting these here more as a reminder as things go on. If you're confused about a measure or want a reference on something, you can go up here and do help. All right. Because I'm bridging Maria Christina and Molly, we're going to do our metadata roadmap to get our data where we need it to be just one last time. And you get to save this data set and not do it again for this session. So first of all, I'm going to get this file. There are multiple ways to do it. You could also read it in through here, but I want it named a certain way. So we're going to hit run. As Maria Christina noted, you don't always have to highlight things. I'm doing it for clarity. So I'm going to get out of documents really quick, find my...
Just a reminder, while John's looking, if you have any stumbling blocks or questions, raise a hand and any of the...
Thank you, Molly. I was supposed to say that already. Let me make this just a bit bigger so I see what I'm doing. Where is desktop? There's desktop. OK. Too many folders. Oh, but I don't actually probably want that. Oh, good. And I'm going to go down, and all I have to do is highlight this. Where is it? There it is. OK, so I should see this data here, 7,581 observations. Good to go. OK, so we've imported data quickly. We're going to focus on community 7. There are multiple communities. And 3 major steps. So this is talking about that roadmap, right? So in this data, because I'm using a curated data set that has clear node IDs and the IDs are numeric and I'm not having to deal with character variables, I'm going to create my edge list first, and then I'm going to make my node list. My big steps going to this roadmap are in these big blocks. So creating a list, I'll talk about the steps really quick. Then I'm going to add attributes. So those are my 3 major milestones as I'm walking through this. If I had text data, I would need to make the node list first and get numeric IDs, then create the edge list, so forth and so on. But these are the 3 major components. So I'm going to make my edge list. First step, I'm going to select the variables I care about with the select command. Then I'm going to filter to only community 7. That's what I'm doing here. Okay, and I see that I was successful to this extent because I see these observations 457 and 12 compared to 7,000 something and 38 variables. And I can open this just to clarify one more time that I actually got what I wanted, right? I'm coming down here. I'm gathering this time because my alters are across multiple columns and more sort of a matrix-y kind of layout or a conventional data set. So I'm going from wide to long. That's what I'm doing in this step. And if I unpack edges really quick, I can now see that I have this alter value. Alter label is just referring, I have to put the column label somewhere. Value is the alter IDs. Again, we're going to get to looking at this network in just a second. I'm just going over these meta things one more time. We're having edges. I'm just getting rid of the 999 values. And I'm going to label ego NID, sender and target. Why am I doing that? Because I want to be clear about the directionality in this graph. I think the directionality is meaningful in this case. So I'm going to indicate that in part by the labels I use. All right. So that's happened because I see sender and target. Maria Cristina is probably shaking her head right now. Why aren't you inspecting your data, checking for missingness? Bad, bad, bad. I'm just going to say that I did do some of that before doing this, I promise. All right, I'm creating my node list. I'm making this I'm making a numeric IDs in sequential order. The reason why I'm doing this is there may be alters that appear in my data but weren't surveyed directly, maybe because they refused to be part of the survey, but people are naming them. And they still are important for generating network qualities. So I'm just doing that here. So this is second major milestone, making the node list. I am getting rid of duplicates. So I have a complete list, but I don't have redundant values. So that's what I'm doing with this distinct command. And 440 is looking good. Okay. I'm going to now get my sequential ID. I'm going to do that by using the row names. By default, the row names are numbers, but unfortunately R is mean to me and makes them a character variable. So the second thing I'm going to do is make it numeric so that I can manipulate it, potentially. So that's what I'm doing here. Last step. Well, almost last step. I want to add my numeric variables into my edge list so that I'm actually referring to my numeric values. So I'm going to, I'm renaming the node sender to ego NID just for the purposes of merging, and then I'll rename it back. So that's what I'm doing in this step. I'm going to join my data. Left join means that I'm joining just to the left column. And again, remember in the orientation slide, there's a big thing that talks about joins. And Maria Cristina, yes?
I think I've seen the same mistake.
Ah.
Error about here.
Okay.
Something that's coming up with line, unused argument for the, yeah, okay. If you line 47.
What, the deprecated triple or
No,
what?
so if you scroll up in your code.
Okay.
Line 47 or so when they're making the edge list.
Yeah.
Yeah. So a lot of people are going to
Let me just do it
Right
and
there,
then see.
So that code
Right here?
all of step 1. Yep.
Yep, all right.
Has somebody solved it?
So it's working for some people.
Yes. So we're kind of confused about why it's obviously working for you.
Okay. So let's pull up packages really quick. Let's do a couple of checks. So first of all.
Okay. So I think we might have a solution. So some people it's a dplyr dependency. So it works if you're using dplyr. If your machine's trying to use something from like the stats package or base R, it's not working. So if you tell it explicitly to use dplyr, it works.
Yes.
So thank you, Emily, for solving that. And what's the code to? Oh, so if you're doing the, so if you use like dplyr : it'll.
Okay, up here.
Emily has the code if we need to ferry it up to you. Or if anybody else has another clue. But
So I think it's this, right? So what you need to do is say not only read dplyr, but library : package. Is it package : dplyr?
she did. She has it a little bit differently. Right? Does that work? Does anybody know how to make it?
John, what we do also, if you load dplyr as the last library, it will by default. So if you guys see that library list right there, if you put dplyr as the very, very last,
Here, we'll do this.
it will say, hey, select is coming from
And let's
dplyr.
actually confirm that it happened. So if I type like this, dplyr should be checked. If dplyr isn't checked, it means it's not loaded. And actually a graphical way to load it is literally just to type in like this and then hit the checkbox. So our surefire way is dplyr : right? Confirmation, right? Yeah. This is, so if you can't get it by loading or by selecting it graphically, you can also try it that way. So do it, well, I'm going to get it, so that's kind of a false positive. But people type in dplyr : is that working for you? Okay, cool. You know, we can do this slow enough that we can make this happen. All right. So then in gather, it's going to be the same thing. Each time, this actually is good because this indicates the syntax, right? This is the command. You just have dplyr in front of it, : saying, I'm loading this package and I want that particular command. Okay? Why don't we give people, because it's the same thing over and over again, we're going to give people about 3 minutes to just do your dplyr. And the people that have things loaded okay, just sit tight for a minute or two. And then we'll come back, right? Because we want to make sure people can follow us. I suspect, by the way, you should beware people, social scientists, that have their pet theories. But my pet theory about this problem is that depending on the version of R you have, dplyr is going to have some things loaded and some things potentially not. And then in that instance, you have to be very specific about what you're loading. So this may be you have a slightly older version of R, but again, beware social scientists and their pet theories. All right, so let me go up here, and I'm just going to do the same thing. So, okay. That one probably doesn't need that, but okay, why not? Yeah, it probably doesn't actually need that. This not a dplyr command. Okay. Let's see. I'll just fill this out. Oh, need to spell that correctly or this isn't going to work. Okay. All right. So I've got my little dplyrs in. How's everyone else doing? People got their dplyrs? Okay. Molly, what's the situation in the room? We're good? Okay. So where were we at? Let's see. So I think, can people, if you run down to removing attributes down to here, when people do that, are they getting two files that look like something sensible? And let me demonstrate, I guess I'm going to demonstrate what that means. So I'm going to start up with my, I'm going to begin up at the nodes list, and I'll start from that, and then, okay. Tidying up. All right. Okay. And then I'm going to merge attributes. Hopefully I spelled dplyr correctly each place. All right. All right, yes. So did I actually merge attributes? Okay. So when you open up your nodes file, does it look like this? Yes? Yeah? Okay. How are people doing? Okay. Yeah. So I've ran down to step 4 where I'm going to remove the attributes. So I'm basically done. And I'm going to remove these attributes, and we're going to save these and never do this again. So I'm going to remove attributes now. And I'm going to save these files. So this is the file I'm pulling. This is what I'm going to call it. And because, oh, have I set my directory? I don't know if I've set my directory. Well, we did not set our, so we can set our directory. Before we save these things, we need to save them somewhere. All right? So we can do that by new project, reopen. No, I'm importing. Where is the set directory? I always do this by type command.
Go to session.
Mm-hmm.
Set working directory.
Yep. Right here. And then I'm going to choose my directory, and I'm going to hit Browse. And in my case, I'm going this PC, desktop. Now, whatever. I'm just going to do the desktop, frankly. Okay. So now we're going to actually look at our network. We're going to actually create a network object. So this step should not be as problematic.
You can enlarge this window.
Okay, I will make this a bit. Oh, to me.
You don't need this.
Yeah, okay. All right, so to create my network object, I'm going to convert these to character because that's what the SNA package requires me to do. So it's just a really quick step. I'm coming down. And this is the step where I'm actually making a network object. Well, let me highlight it. I'm going to move this over just slightly to make it a little easier. Okay. I cannot find negative order. That means I did something wrong. Uh-oh. Probably because of... If people had this error, I'll show you, I think, what happened. Oh, wait, because my HS edges is weird. Well, I'm going to need to back up. I'm going to remake my edges file. Okay. Then let me do this step. Let me check my edges file. Oh, I think mine's getting, I missed a dplier. That should work. Sorry about this. I'm just going to walk through to make sure because adding these dplier commands in my case may have created more. Okay, so that's my initial edges file. Object gather not exported. Oh, that's because that's tidyr. That's why. Okay, good. So people that had problems with the edge file, when you're gathering, that's a tidyr function, not a dplier function. So you're going to need, if you're doing this package double colon thing, then you type in tidyr there. Filter, select, and rename are all dpliers, so that should be okay. And let me check the data set to make sure this looks okay. That's looking better. Sorry. All right, gather's not going to be a dplier thing. That's going to be a tidyr thing. Like that. Select is a dplier, rename's a dplier. Check the nodes. That looks right. That's my comprehensive node list. Oh, it's good to slow this down a little bit. Distinct is a dplier command. That's OK. Notice that now I've got down to my 440 edges. That's OK. Dplier, those are all right. OK. Check that. That's actually the case. Sender ID, go ID. Yep. Rename's OK. So if I look at my nodes, yep. What's up? That's OK. That tibble is just a weird.
She has trouble with upper steps. Can you just go up?
OK.
Here it is. So we can see up here.
Okay. All right. Let's check that I actually got sender. Checking, yep. Renaming is a dplyr thing. So we're good on that. This should be a dplyr thing.
This is an odd potential fix, but it's something that happens, and it's also worth knowing. So when you're moving data, or when if you're copying and pasting R script from the internet or from other locations, there are times where your quotation marks or other characters go from one type to another, and that can really cause R to kind of misread what you're trying to type to begin with. So you can see, if you guys look at your kind of single quotation marks and a lot
and
of
the rename statements. For people that are having problems with the rename statements.
Rename or select. So what I would, in your code, you can see that those single quotes are actually, there are two types of single quotes. There's one that's right next to your escape key, and there's also one that's right next to your enter key. And R usually just handles the type of single quote that's next to your enter key instead of that escape key. And believe it or not, they're actually different. They mean different things. So if you want to hit Control F or Command F if you're on a Mac, and go to find and replace.
Find. I'm not going to do it because I think it's going to mess up my PC. But if you're running a Mac, you can then hit this.
Right. So you want to find the single quote next to your escape key, and you want to replace it with your single quote next to your enter key. And you want to do that everywhere in your program.
Ouch. I did not know that was a problem between the two. I'm going to do, for the sake, because this is actually a descriptive statistics lab, I'm going to finish this object. I'm going to upload the R sets, and then you're going to download them. And we can work, people that have problems with this, we can work through this so we can get to the descriptive part. So let me just get us to where we need to be, and then I will get that data set up there for you so we can move on. I think while I'm doing that, DNAC RA is working through stuff. That's super helpful. Just want to make sure that so let me run this. Okay. Yes, that looks right. And let me check my nodes file. Right. Before I save it this time, I'm going to do this. And I'm going to run this. And I have a network. OK, so this means that this code, I'm going to send you these R files now. All right. So just go back up to here. I'm going to upload these. So do people now see, you should see AHS edges and AHS nodes in your Dropbox. Everybody got them? All right. For people that have problems with this step, feel free to talk to me later on today about working through this stuff. I'd be happy to do that. OK, so everyone got these on the computer, got it in your work environment? You see it in here? Yes? Shake heads. Yeah? OK.
Sorry, the quotes thing completely worked if people closed out of the R session, got back in, and then
We'll do it later. We'll take care of it later. We have an announcement about the quotes thing, but let's get to the lab. All right. So has everyone got a network object based on those two scripts? Or should I run that script again? Again, shake your heads if yes. Yes? Good? How about over on this side of the room? Is this OK? OK. All right, so we're going to look at descriptive statistics in R. First, I want to start with like a little candy. After all that pain, I mean, Lord. OK, so first of all, I just want to inspect this network item to make sure that we've got a network. So 440 vertices, that checks out with my nodes. I don't have any attributes loaded yet. These edges check out with my edges file. Things look copacetic. We're good to go. So I'm going to create 3 measures. These correspond to, they're node level measures. These correspond to what Molly was talking about earlier. I'm doing this for the sake of visualization. I'm going to talk a little bit about implications they have when you're doing network analysis. So this first little object, this is Eigen. Eigenvector centrality, remember, refers to being central because you know other central people. You can be that, but not be the most central person. A good example in the real world would be, think of actually, it can be kind of the inverse. Think of a personal assistant to a CEO. That personal assistant in a network graph could be highly, highly connected, but actually, the CEO is connected and kind of hidden behind the personal assistant, right? So that CEO might actually have a high eigenvector centrality because they're connected to the assistant, but not actually have a high total degree centrality, right? So we're going to make Eigen. This is just a little vector of items. This command here, just to review syntax, this is saying SNA package, calculate eigenvector centrality for this network object, AHS network, okay? And you should see, if you scroll down here, this is a vector, so this is appearing as its own set of values. And good thing, this matches the number of vertices I have, so things look okay. So I have an eigenvector centrality for everybody. Indegree. So Indegree is just a little bit different in that we have the command degree. This is our network object. This is the mode. So we could have in degree, we could have out degree. So we're going to type in degree. Remember, degree centrality is that I'm receiving lots of connections. This is generally, in my experience, a more reliable form of centrality because you can be like me and part of the Hopeless Hearts Club and nominating everybody. Right? So I'm going to do degree centrality. And if I scroll down, did I actually do it work? Oh, what happened? Let's see. Let me try it one more time. Oh, it looks like I cut something off. What did I do? So edit, undo. Oh, no, that wasn't right. Let's come down here. OK, let me try it one more time. Yes. OK, and there's Indegree. Good. Now, what am I doing down here? This is a visualization thing. Jim's going to talk about visualizations. Again, this is just to get the candy, to get to the rest of the descriptives. But it'll be helpful because we can use this to also think about different concepts. I'm going to actually multiply this by 0.15 because the Indegree values I'm going to get are so big that the nodes would be super huge and the network really wouldn't be sensible. So I'm reducing. I play around with this a little bit, but I'm reducing this by this value. They'll be proportionally correct, right? Because I'm multiplying all Indegrees by this constant 0.15. And I'm just doing this as a visualization practice. And this may be something you have to do, so I'm just bringing this up really quick. I am creating, we can do the duplier thing really quick. I am creating a set of nodes, call them female, so that I can color them. This isn't absolutely critical to, actually, we're going to, well, all right. We'll try. Dplier, colon, because that's a clear dplier command. We're not doing any, I don't think there's any weird tilde stuff. And I'm going to do dplier. And what I'm doing here is I just want to color, I want my network to be sensible. So I think gender is important in school networks, so I want to color the nodes by gender. But I might also want to color them by race. So I'm creating 2 variables that allow me to do that. This color race and color female. I'm just using this very basic logic. If else race 5 equals 0. Race 5 is my race variable. I have gold, and otherwise I have it as a different color. And I basically go down all the different values that I could have as my different racial groups. I'm just going to run that quickly. All right. So this is, I'm making these vectors so that I can assign them to the network. So This is, if you have your own data set and you want to color it by the nodes you want to color it, this is practice for that. I do not think these are things that require, these are base R kinds of stuff, so I think we'll be okay. Well, yeah. I'm going to set vertex values. Now I'm saying, hey, I'm connecting this value, like the gender, to the vertices of the network. So I'm assigning to each vertex a gender, and I'm assigning a race, and then I'm assigning a color, and a color female, and I'm assigning Indegree. Why would I have gender and race, and then a colored race and female? Well, maybe I want to tell the stats package that specifically I want this color. I don't want a default color that you want for me. I want to specify the color. This is a way to do that. So I'm going to run that quickly. I'm going to check that my attributes actually got loaded. And I can scroll up to the top of this quickly. And we have that's the edge list. 440 values, attributes, actually. Yes. There's my race attribute. There's my female attribute. Good to go. And then I'm going to visualize this network quickly. And then we're moving into seeing if this network makes any sense. Oh, actually, that was pretty amazing. So I'm going to zoom really out so I can hit the zoom button to get a better sense. So does anyone have a sense of why we might have two really distinct components from each other in this data? This is community 7. It's because they're different high schools. So we're not, by design, we're not asking people to nominate people across different high schools. So we're going to have one high school, another high school. And then what these topo marks are telling us is this is colored by race. It's size by Indegree, so that's how many degree they're receiving, how many connections they're receiving. The fact that you have these two distinct sort of hilltops here, more dense parts of the network, those are gender. There's a boys click and a girls click. Okay? And if now let's sort of think step back a little bit. So we've talked about this concept of nodes or vertices. That can be people. That's what we've been talking about the most in these examples. But that could be organizations. That could be anything that has a connection between them. One thing that we've talked about, but there has a slightly more formal definition, we talk about this concept of a tie, but ties can be an edge or an arc. An edge is an undirected tie, an arc is a directed tie. And why that's important is that certain network measurements that we're going to be doing, they depend on the assumption of whether the network is directed or not, or symmetric or not directed. Okay? So formally, a set of vertices and edges is a graph, and a network is a graph that has attributes. So node labels, race, gender, things like that. So if someone says, well, that's a graph, that's a network, I mean, most of the time we sort of think of a network as something that has attributes, but this is just to be clear about the language you use. A graph is an undirected set of lines and vertices. A digraph, directed graph, is a directed one. We're just going to do some really basic diagnostics. This would be more like, okay, did just my attributes and nodes load in correctly? But the size of the network, when someone refers to the size, they mean the number of nodes. So I'm going to run, I see 440. Sanity check, that seems okay because that matches the 440 observations in my node list, right? Okay. Edge count. So far, these two we basically already have this information, but this is good, 2,099 edges. And that should correspond to my edges in my AHS edges file, right? First new piece of information, dyad count. We're going to run this. What this tells me, just to give a little context, is, but we also have this visualization, that this network's a pretty highly connected network. I mean, jumping from edges to dyads, the ratio of those things, and we're actually going to calculate that ratio of connected dyads to null dyads. This looks like a fairly connected network, which leads us to this idea of density. Okay? Density of a network is the number of connections over the number of connections possible, right? Let's talk about that a little bit. So we have HS network. We're going to say it's a directed graph. That means we're saying in this network, the directionality matters, and we want to include that in the calculation of density. So we're just going to say what mode it is. And each time that we run these metrics, we should really think, does the metric assume a directed or undirected graph? That should be like a red flag question, like, okay. So I'm running that. Now, so this gives me this density value, but let me give you a little context. Density matters depending on the context that you're visualizing, that you're running your network analysis on. In human networks, social networks tend to actually be relatively sparse. That's actually one reason why we don't use matrices and we condense them into edge lists, because we have a lot of empty cells. There's social processes and psychological processes that basically make it that not everyone's going to be connected to everyone else. But if you were doing, for instance, medical records or text networks or other things where, or you were doing proximity network, like if you said, oh, I belong to the baseball team, and everyone, you basically interviewed everyone in that baseball team, and they were all like, oh, we're all on the baseball team, and they're maximally connected. One, you don't know the direction of that tie because it's just through a membership. But two, that would be super high density. So you want to think about what the context of this density value means. But this is a human social network. It's a directed network. This density value makes some sense. So degree distributions. So we're going to get our in degrees. So that's, again, remember, those are the ties that people are receiving. Out degree, those are the ties that people are sending. And StatNet is kind of a stickler. StatNet's like, you want in degree, out degree. Well, you're going to have to add them together to get total degree. But let's get a little histogram. So that's what I'm doing down here. This is just a little basic R stuff that says I'm making a table to build this histogram. I'm getting my in degree, I'm getting my out degree, and then I'm going to add the two to get a total degree. And let's look at this. And let's zoom out a little bit. So this in degree is sort of our classic fat tail distribution where there's some people, there's a lot of people that, well, actually, does that mean there's a lot, am I reading this correctly? Hold on a second. Yes, right. There's only a few people that aren't connected to anyone. And in this network, there's a lot of people that are connected to a lot of people. Well, that's actually, usually it's you have someone, am I reading that correctly? No, this is a person with 20 ties. Thanks, sanity check. Person with 20 ties, person with 15 ties, person with 20 ties, not so many people. And as you get farther back, and there isn't actually a zero in this network, everyone's at least connected to one person. It's probably actually a value of 2. We'll get a little bit more specifics in a second. Notice I want you to focus on the shape. The out degree, it's much more uniform distribution. And its total degree is obviously just adding the two together. But that tells us a little bit about human nature. People tend to report. Let me actually reduce this. So let's talk about paths. Let's talk about walks, paths, shortest paths. Walks in a network, and this is important. The concept of walks actually will be important later in the week when we're trying to impute things. That's assuming people can do a random walk through a network. What does that mean? I have some text in here describing that, but basically it says that edges and nodes are connected to each other. They can be connected, I can be connected to J, J can be connected to I. They can be through repeated nodes. It can be through repeated edges. A path implies directionality. I is connected to J, J is connected to K. And all the ties, well, actually, what it really makes a path is that all nodes and ties are distinct with each other. And then the shortest path, obviously, is the most efficient path between any node I to any node K. And when we say we're calculating the average path, what we usually mean is we're calculating the average shortest path. And that's important because that can give us a sense about, if we're thinking of networks as pipes, they can give us a sense of how quickly information can be distributed across this network. So in this case, we're just making this little object, AHS-geo. That's to refer to geodesic distance. That's just another term for saying shortest path, okay? So I'm going to run this really quick. I'm just going to confirm that I've got it. All right, oh, there's a lot going on there. So I want you to actually do something with me right now. We're going to make, so keyboards, a little interactive. AHGO, like this. And then we're just going to do as data frame, AHS-geo. And I think that we should be able to see this. And we should see this down here. And I'm just doing this because I'm kind of old school, and I'm used to looking at things in a kind of a tabular format. It'll take a second to load, but it'll be there in a minute. And this is what's going to be displayed here is the number of counts. So essentially the number, whoa. So person 1 is, this is the number of counts that this person has to a number of paths, sorry. So paths, so for person 1, 1 path of 1, 4 paths of 2, 3 paths of 5, etc. across this list. This is just to sort of help you interpret, because when it comes out on the here, it's a bit of a mess. Okay. But we can get the shortest paths. I'm going to run that really quick. And we can get the number of shortest paths, which is pretty interesting. And we're going to make a histogram of that. Oh, why am I getting? Could I? Oh, that might be. Well, let's. Yes, it is. So I'm going to rerun this. Thank you. Run. Let's try now. Why am I getting no? Rerun the top. Check that I did it. Good to go. Go down here. This is to get the length for each person of their shortest paths. And this is to get the counts, the number of paths. And then we can make sense of this by looking at a histogram. So path 0, though, doesn't, that's because we have 2 high schools that have no connections with each other. So they're inflated in this network because we know they're not talking to each other. But if we look at the average, if we remove those zeros and we think about the center of this distribution, that's roughly, what, like 4.4, 4.5, somewhere around there. That makes sense. And actually, I calculated this in iGraph to get a sense, because you can't get this in StatNet quite as easily, and it corresponds to the center of that distribution. So this is getting us a sense of how many jumps does it take to get information, or to connect to what Molly was talking about in the 6 steps of Kevin Bacon in this network. On average, they're connected by 4 steps across the whole network. So this idea of transitivity. So transitivity is we're getting the sense of the ratio of closed triads to open triads. And again, we're just using this gtrans command. And our ratio of closed to open is roughly around 20%. And the default is weak transitivity. There's a strong form and a weak form of transitivity, and I defined that a little bit more clearly here. But in the weak form of transitivity, I is connected to J is connected to K, but they don't have to be on all transitive ties symmetric. Like it doesn't have to be mutuality. If we do weak, we should get exactly the default value. 2, but if we did strong, oh, this will actually get us our weak senses. Hold on. If we did strong, we would get a different value. If you did measure equals strong, we can get our senses. And this is how many, literally, triads, closed triads we have in this network. So this is a count. OK, I put images for these tests, because these take a little bit to run. So some people might have leapt forward and ran, and there's a stop sign going on for a while. If you did, it's OK. But what this is doing is saying, well, all right, but we have the number of triads, we have this sense, well, is this transitivity, which is the sort of the base level of modularity, is this clusteredness, the groupiness, is this more than we expect by chance? So we can do 3 kinds of conditional tests. We can do by size of the network. We can do by edges, and we can do by dyad count, or by number of dyads. And if you look at the images, the results are that by size, it looks like this is greater than we expect, but not by edges or by dyads. So this is not, which actually is a little surprising to me, because I think it's a pretty connected network. But the main idea I want to introduce there is when we're trying to assess, oh, does this make sense, like within a statistical framework, what we're always comparing it to is sort of a random null model. And this conditional tests that are up here is sort of the most base level of random null model. Mutuality. Mutuality is symmetric, reciprocation. So if I hit mutuality, this is 400 out of my dyads, 450 mutually reciprocated dyads. So that's a lot smaller than number of dyads. Oh, so there's a lot of people that think they're friends that the other person didn't name them. Now there can be a lot of reasons for that. It could be I just happen to forget about Joe, or or it really might be that they're just not different. In a social network context, when you're thinking of people, that can be an indication of a strong tie, and that can give you kind of connections in the social support literature about, okay, is this when we're sort of classically thinking, though I leave the presentation yesterday somewhat challenged this, the network of people I discussed important matters with, classically we would have thought it was this group of folks. But apparently they talk about frogs with random strangers, so oh. All right. We can also get the dyadic ratio. This is the one where you really are like, oh, is that sad? Well, this one doesn't look so bad. So this is dyads, I to J, J to I. Oh, there's actually a lot of love going on in this one, so that's not so bad. We can do edgewise ratio, reciprocated edges, all edges. That's smaller. Well, that's okay. So this triad census. All right, I have to be a defender of the triad census. That's partially because I'm a social psychologist, and I actually think structural balance theory is real. But from a network perspective, this triad census can give us a sense of how the network's going to break up. So we think of triads as these base units of groupiness, and we think about a triad, especially if we actually knew who liked who and who didn't like who, we could get a sense of where this fission line is going to be in the network, but we can also get a sense of hierarchy. How hierarchical is this network? And because if, for instance, if we look at these different types, and notice that like 0, 2, 1, 0, A reports to B, C reports to B, B reports to no one. That's that indicates to me that that's potentially a more hierarchical network. So if you looked at we can look at the triads across the whole set, and we get a sense of like the flavor of this network a little bit. This one we can also make an object. I don't have anything after this, so this shouldn't mess this up. So again, we can type this. We can just say triad, right? Arrow key. Actually, is it? I think I wanted the other arrow key. Do I want the other arrow key? Yes. Nope. You get up here, you lose your mind. As data frame. And again, this is just so I can visualize this. And I'm just going to pull this, Control copy, Control V. Okay, and we can look down here just to get a little better sense. So this is null triads, but we can link these up to the different types and begin to get a sense of an intuition about how reciprocated our triad structures are, or how hierarchical they are. But we can elaborate this by beginning to look at a meso level how groupy are by looking at the components, looking at the modularity, and then we're going to get to that fun concept of K-cuts and K-core, and all sorts of good stuff. So we can do two kinds of components. We can do weak components or strong components. Strong, I'm going to make this a bit bigger so people can read this. So if we look at, and I give the pages, if you look at that purple, Wasserman and Faust, the page numbers are there to look at this yourself. But for our weak component, notice that the directionality, I is connected to J, but I is not connected to K. But here, I is connected to J, J is connected to I, and it's a nice clear-cut thing, right? What does that mean? What happens? Well, if I do the strong version of this, I need to highlight all of the word component. What happens? I get 73. That's because I'm using a stricter definition of what a component is. I'm saying, well, it has to be a direct, component has to be connected to a directed path. If I do a weak version, then I'm OK with a semi-directed path. 4, that's awfully like that visualization we had earlier with those 4, and we'll see it again, of the network. Basically, when we plot this out, you had the 2 schools, and we have some people sort of floating on the outside. We can get, if we want to know the list of nodes, which can be helpful, that belong to each component, I'm just going to do strong here. You can do the same trick I did earlier and turn this into a data frame or something like this. But if I stretch this out, the first part of this is going to give me component membership, but there's actually a couple of different elements going on here. So the first part gives me membership. So if I run this, I'm just getting the segments of the list. The second part gets me the size of each component. Oh, why am I? Let me do this. If I go too fast, bad things happen. So let me run this again. Right? Let me run this. Right. Let me get the size. Right. And again, you can move this into different structures, but we have one component. So this is getting us, remember, this is a strong version. So there's 73 of these or so. So the first one's got 211 members. And then because we have a lot of people that aren't connected directly through directed paths. So we're getting some awfully big stuff, and we can get the distribution of component sizes. Cut points. I love cut points. That's because I'm evil. If you take a network, cut points are how to break it up, right? There's actually a lot of work that looks at how fragile a network is. So in cybersecurity, how robust a network is. There's a trade-off in networks. So there's efficiency, which is information going through with the minimum number of paths to maximize the throughput, as opposed to thinking of like the inside of a baseball where you have a ton of connections, but that's also, if you're an organization, that's a ton of connections that you're supporting. Those come typically with costs. But on the other hand, that means also with more connections, that's more resilience. So cut points in organizations literature often is kind of connected to this idea about how resilient it is if you removed a node or if you remove an edge from the network, what happens to the network. So the first thing we're going to do is we want to find our people that we would like to cut. So we just do cut points. And what this is this is a list. Oh, let me go up. Person 11, I've marked you. But let's plot this really quick, just for a second. And this is saying, hopefully this is large enough. Gives us a sense pictorially of our graph again. Let me make that a little bit. Hopefully I didn't do the same thing I just did. What is this? Reduce. All right, I don't want to close this down. Somebody and DNAC team, I'm just trying to reduce this graph, but I seem to be like in this mode. This is our studio. I just want to get out of the graph here. So while we're here and we have it so zoomed in, the red and the green are indicating the cut point values. You should see green nodes and red nodes. The green nodes say, if you got rid of those nodes, you would break the network up. So let's do it. Let's get rid of a cut point. I mean, it's sort of, I viciously enjoy doing this. I just like watching kids groups just fall apart as I find the key kids. It's a good thing I can't have no identifying information and I actually obey I or B. Cool. Now, yeah. So I've made this list, this object AHS cut from the AHS network 11, and now I'm going to do this with my 74. It's just identifying the stuff. When we're talking about bicomponents, bicomponents are graphs that are connected by at least two, or connected to at least two others. You can run that, and this gives us membership in the bicomponent. Can do k-cores. Hold on a second. Right. We can say, OK, I want you to be people who received.
What's a k-core? Why would we do that?
So k-core is, in this case, we're saying I'm looking at think of a network as a set of Russian dolls. So the first most outside layer is just connected by 1, then connected by 2, then connected by 3. Or you can think of it as sort of drilling down. And we can plot that. And we're saying I want everything that's connected by 1. And that's our network. But we can plot it here. If you make it larger, I believe you'll see multiple colors indicating your k-core membership. And here we can say, well, I want you to at least be connected by greater than 3, so you must have a degree of more than 4. And watch what happens to this poor network. So we've got the sort of internal groups of people. One thing I actually want to say, I targeted poor 11. I did confirm I got rid of a component that way up there. Actually, if I go to my log, I kind of missed that. So if I go back up here, all this stuff, membership. Well, when you run it yourself, what I encourage you to do, you can do AHS cut here, 11. You did have 74. If you read this, it was 75. I think maybe because I already removed this person. But in any event, you'll see a difference in the number, I promise you. Now, we're doing clicks. Someone remind me what a click is? Audience participation, please. Yes! Now, one quick question about that, though. Is it direct? Are they connected through directed ties or symmetric ties when you think of clicks? This is like the advanced extra goody question. When you're thinking of clicks, you're going to make the network symmetric. So one sort of reason why we might not want to think about use clicks, I mean, there's good times to use clicks, there's not, is I'm losing some information with these click measures because I've got to transform the network into a symmetric network. That's where this directed false thing comes in. Dun, dun, dun. So I'm doing that. And we can get a click census. And this can give us a sense of everyone's membership in a click. Again, and you could output this again as a value and look at this, and you could get the number of clicks. So let's analyze this just a little bit and go, oh, wow, that's a lot. It's just a bit bigger. So person 7, person 10, person 67, 73, 323, and 346 are in a common click. And you can run up through the list of clicks, which gives you a sense of that this is a pretty highly connected network. We can get a click count. We can know just how many clicks. Oh, what's that invalid state? Oh, no. What did I do? Do not try. Maybe run this again just to make sure. Okay. Okay. This gives us literally like the output of clicks to people. And there's a lot more you can do with clicks. You can get, I think this is in some ways the most useful. You can get the clicks by their number of size. So you can get a sense of like what are the largest maximally connected groups. And we've moved from, because there's been a lot of craziness, let's recap just a little bit. We moved from system level measures, density, average connectedness through shortest path. We drilled down to meso level, so we were thinking about transitivity, and we've been thinking about clicks and components. So this is basically these structures within the graph that are more connected within the terms of a component, more connected to each other than connected to other people. We're going to bring back, for these node level measures, our directionalities. That's what we're doing here. And we're going to talk specifically about, so reachability. Again, Molly did a very nice visualization of reachability, but that's the idea of any node who are the subset of nodes that they are connected to. An example, interpreting row 2, we can do one really quick. And then I'm going to skip down through some stuff because, again, there's a lot here and we've had some technical difficulties. But if we interpret here, 2, we can reach, let's say, 2, let me go up. I think 235, right? This just to give you a sense of how to interpret this. So node 2, the node can reach node 235 through 235 paths, whereas the middle, well, I'm going to skip this. But the sense is, this gives you a sense, again, of we've done a lot of measures of how is information flowing through the network. Can move this into a structure that might be a little bit easier of a list. And we've talked about degree. We've talked about out degree. Talked about total degree, so we're going to skip that. Closeness centrality. Does anyone remind me about closeness centrality? That's nodes are how close nodes are to each other, right? Sort of implied in the measure, but it's a directed measure. But closeness centrality is kind of a problem child measure. So let me visualize that for you. Why do you think I'm getting it? I got this error on purpose. I know there's been a lot of red. Because we have 2 high schools that absolutely aren't connected, and the distance between a path of 0 is infinity in graph space. So we're going to have to fix this. So we create a little function, and that's what I'm doing here, to basically go, okay, we're not going to include that the zeros. We know that that's going to throw that off. And now we can get a histogram that makes this make, well, let me do this again. Closeness. I probably didn't highlight this all or some such thing. Okay. This should not work, and then the next one should work. Yeah, we know there's an error because we have this infinity problem. Let's go back here. Okay, good. Right. Well, I'm going to do this one at a time. And then our histogram. Oh, it's too big because the thing's not big. Oh no. Do I really want to do this? This is scary. Okay. And that makes a lot more sense. So what my little function was doing is basically saying, hey, we know that we have these 0 paths. We're taking that into account. But this is giving us a sense that on, what does it look like? On the average, it's what? 4 to 50? We have info centrality. I think I'm going to let you guys do that. Betweenness is a really important measure, so we're going to do that really quick. So this is the idea that a node is between other nodes. It's basically, you have a node, lots of paths are going through it, and we think that that means this person has a particular control over the flow of information. So what we can do, this is a somewhat computationally arduous measure, but in a small network like this is not too bad. And we've made this, and we're going to get a histogram again to make this a little more interpretable. And so there's a lot of people that aren't between anyone. And then as we have a few people that are between a lot of people. But let's actually visualize that now. What would that look like in a network graph? So we'll do that. I'm not going to make it big, but the nodes would be sized by betweenness. And so we have some people that are between in the sense that many, many paths are going through them in the network. And I wanted to highlight the connection between betweenness and closeness centrality, because they're related concepts. So, but not surprising, nodes that are close to each other in the terms of distance and paths also happen to be nodes that are in this network that are having many paths intersect, so they're between many other paths. So it's not surprising that there's a correlation, but I just wanted to show you conceptually the relationship. We have eigenvector centrality, but let's get to positional analysis. Okay. So we have this concept of brokerage. Brokerage in this sense, so there's actually kind of two competing versions of brokerage out there. Well, there's many versions of brokerage, but there's Bert's mention of brokerage, which is this, it's connected between a centrality. So if you're a person that happens to be between a lot of other people in the sense that many paths are going through you, if you are a person that happens to bridge a hole in a network, that's particularly valuable, right? Because essentially, important information may be going through you. That's the Ron Burt version. This, SNA doesn't actually support that. I think iGraph actually calculates that directly, but SNA package says, okay, but in terms of what? So it asks you to put in an attribute. So in this case, race or gender. And what it's saying is, okay, out of the group of people that share the same race or share the same gender, are you a broker in that group? So this measure is a little more specific in that it's saying, okay, in what sense of what group? It's implying a group level attribute. So I'm going to probably because I don't, I may not, do I hopefully have race in here? Okay, so let's make this, I might have just skipped. Let me go up one. Oh, I hopefully, let's check this network quickly. All right, HS network underscore. There's been so much madness. I just want to make sure that the attributes are actually there, or this won't work. All right, so we can assign our attributes quickly. Not a problem. We have the network. It's OK. So we'll go up here really quick. Merging. Have the attributes in the file, just need to put them into the network. Don't care about these, do care about these. So gender, race, this stuff I care about. Oh, why am I having a problem? Oh, because I tried to make it a vector before making it a thing. Hold on a second. Okay. Done that. Making that work. Right. Good. Creating vectors. Good. Setting vertex values. And a summary. Go up to the top just to check that I got this, and then we'll get back to this concept of brokerage and structural equivalence. Yes, they're there. OK, coming back down there. So here, race. So this is, and I have this defined in the code, but we should get a histogram at the end of this. Oh, probably I made this too small. Make this over just a little. Let's just do this just to make sure everything's good. Histogram. These are different roles people have, and these roles are defined at the top. So by far the most brokerage roles are people mediating within group contact. So there's a fair amount of racial, there's a fair amount of racial homogeneity within terms of friends or contacts in this network. Then we have a little bit of mediating between outgroups, this gatekeeper role. We can combine these different types to get a general sense of brokerage in the network. And we can, here what we're doing is sizing the network in terms of brokerage roles within terms of race. And I won't make it large, unfortunately, because we know what happens. I'm going to first talk about structural role equivalence, because I want to end with what Molly did. And then I can come up to this part of the code that Jimmy Adams actually gave us yesterday, which is pretty cool. But I wanted to stay within SNA really quick. So finally, we were talking about structural equivalence earlier, right? And we were saying, OK, a network, if we can think of roles within a network and we can think of people connected in sort of typical ways. And in this case, what we're doing is you can literally make a network into a string. And what I mean by that is the series of connected, not connected across all sets. And you can get a Hamming distance. You can go, OK, who are the kinds of people that are only connected to one other person? So that would be 1, 0, 0, 0, 0. How about people that are connected to 2 other people? And you get the difference. So that this is just one way. There are many ways to look at how similar people are in terms of their patterns of relations. OK? So that's what this structural equivalence distance, SE dist score, is doing, structural equivalence distance. And this is giving us how similar people are in terms of their pattern relationships when using a Hamming distance as a measure. We can cluster that. I'm going to do that here. And you should get a dendrogram. And that dendrogram is looking at, in terms of the types of people, in terms of the patterns of relationships they have. I know this because I've looked at the dendrogram a little bit before. I'm afraid to make it big, but you should see a branch at the very, very top. And those are the kinds of people that are basically pendants and connected to 2 dyad types. And then you have more connected sets as we go down through. So that's what these branches are, is just, and we're going to visualize that in a second. So this is, we're going to cluster hierarchically. We're going to do it to a depth of 30, which is what H30 means. And again, we can talk about what all this means. We're going to do a block model where we're looking at these patterns of relations based on this hierarchical tree structure. Run this. We're going to make a cool image in a second. And I'm just going to run. I'm going to hope that I can just run all of this. If you make it big, compare this image to the dendrogram, and basically that first big cut you can kind of see is this stuff to the left. And then as the relational structure gets more complicated, those are the things that are connected to the right. So this case, these aren't nodes. These are positions, the network of positions to each other in terms of how similar they are in terms of their relational similarity. So the people that only have one other friend, they're all being clustered together in one position. People that are hyper-connected are being put in another position. Now I want to go through, how much time? Are we over time? We probably are, right? Okay, we're going to go and do one last thing. This actually is going to somewhat prepare for Jim's lab because you're going to have to do the same thing. So we'll get a little training. We're going to look at effective size. But to do that, Jimmy Adams works in iGraph. iGraph. So this is a new package. So we're going to move between SNA and iGraph quickly. So the first thing we're going to do is we're just going to detach. That's because iGraph and SNA do not play nice together. Do not try to run them simultaneously. They have very similar commands. Things get confused. It's bad. So we're going to detach. We're going to load.
Two major network programs in the field wouldn't talk to each other.
Yep. I'm just running iGraph. Look, again, a couple of reminders about why iGraph, how iGraph and StatNet are different. The two major ones that are going to jump out at you are A, when we're thinking about the weight of a tie, iGraph thinks of that as a distance. So a higher number means that you're farther away from somebody, like spatially, like miles or something. In SNA and StatNet, that was built by sociologists, we're thinking of frequency. So that would, a higher number there would indicate, oh, we're closer to each other, or like we see each other a lot, something like that. The other thing where it can be problematic and cause when you're flipping between these two programs is the index number. So does your nodes start at 0 or do they start at 1? And again, this comes back to this idea that this was designed by physicists and computer scientists. I'm just bringing this up because this can be a bit of an issue. So I have my flow edges. Oh, I've got to bring them in because I've had to close this. So I'm going to import. Actually, I'm just going to set directory because I believe I just have them. So I'm going to go to session. I'm going to go to set working directory. And I'm going to choose my directory. And I'm going to go desktop. And I'm going to hopefully be able to go there. Well, it doesn't look quite right. I might just bring it in another way. All right. Bring it another way. Open file. So this is this flow, Florentine families. This is a smaller data set. It should be where? Oh, it's in the shortcut, I suspect. Yeah, where is it? Tuesday, HS edges. Okay. There we go. Open this. Yes. Open this. So I've got my nodes, I need my edges. Okay. Yes. All right. So the first thing we're going to do is we're going to check that everything's good to go with our network. So we're going to make a network. And this is an iGraph notation. It's not very different. That's the one good thing about this. These packages aren't all that different from each other. And if you zoomed out, you should see set of nodes with Italian last names, because those are these Florentine families are competing with the Medicis in the 15th century. And we're going to get the effect size. This doesn't come naturally in iGraph, so this is a really nice thing that Jimmy Adams did. This is, remember, effect size is essentially the number of connections not with taking out ego. So how many connections are alters going if ego's out of the picture, right? And I'm going to highlight effect size. And this is for this function. I'm reading effect size. I read in the function. This is graph G. I just called it G. This is for person 9. Let's change the person. So this person has 11 connections, not if you take out ego's connections. And that's the meta cheese, by the way. Person 9 is the meta cheese. This is the most dominant family. Let's put in 2. See what happens. And 6. Now, we're going to do something a little bit tricky for a second. So we're not going to actually do not do this effect size AHS edges. Well, I guess we can. We'll do that quickly for person 1, just to give a sense that we can do this on a bigger network that's not just our Florentine families. This next thing is computationally a little intensive, so we're going to do a few steps. And this will give you a little bit of practice. We'll run this, and then we're done. Okay? But we're going to practice a little bit, a couple of steps. So we're going to take our data set, and it's AHS. Actually, let me look down at this really quick. Yeah, I guess we'll do that. All right, so first step we're going to do, just type with me, AHS edges. All right, AHS edges. I'm going to go steal some code from the top. I'll be right back. Control copy. Back down. Now assign graph attributes. Let me see something quick. Right. So we're doing, actually we'll go here. So we have, right, HS edges, Control V. Let's get rid of this quickly. This is edges. And then we're going to do filter. And then we're going to do, if we look at edges, sender equals 1. Maybe we'll do sender, we'll just do sender equals 1. This is computationally intensive, so I'm just trying to make a smaller network. Oh. What did I do wrong? I'll look at filter quickly. Sorry about that. Right. Yeah, it should just be that. Oh, probably I didn't. Probably this is a cap sign. Okay. Vertex, effect size. Ah, it's because it's a character variable. Because we had to make it a character variable. Now try. No. Okay. What's up? Yes. Thank you. All right. Now we should have a much smaller edges. Now we still have to make it a network object. Actually, do I do that down here? No. So we're going to go do that. And that says HA. We actually did this above, because we had to make a network object for iGraph. Oh, No, we didn't. Plotted brokerage, warranting families, this. This is our command to make a graph. So I'm going to Control copy. Here's this. Control V. But I don't think I want it to call it G, so I think I want to call it HS graph, like this. Again, this is just a little bit of practice of how to do this. All right. And I don't want it from flow edges. I want it from HS edges. Like that. All right, let's see if I got it to run. I did. Okay. Let's actually check, though, that it did what we thought it did. HS graph. We run like that. Okay, we do have a network. Not a very big one, but I'm actually going to move this down just a little bit. Just to make this a little clearer. So we made this network, HS graph. Now we're assigning sex and grade. Numbers replaced, not multiple, same length. That's probably because I have to filter sex and grade. So I actually think I'm going to stop so that people can get a break. I did want to type through this. The process that you would do is you would filter your attributes also by one to make it match. And I wanted to run through this, but this is really computationally kind of intensive on a big network like this. But what you're getting out of this, which is really cool, let me explain this just a bit. You're getting, so for each ego network, for instance, let's say that you wanted, or each ego, their little network of friends, and you wanted to know within a measure within that ego network. So for instance, what proportion are female? This code allows you to get the distribution variation within respect of how homophilous, for instance, the ego networks are in terms of gender. You could do that by grade. You could do that by race. This code works. You could just literally run this on the larger network, but the thing would go on and on and on and on. So we're going to stop, let you have a break. Thank you for bearing with me through this. It was a little more complicated than I was expecting. But again, thank you. And if you have questions about steps that we've gone through or notation or things like that, find me afterwards. And I expect there's some people with some questions. Thank you very much.
Thank you, John.